Thank you. Thank you, Adisseo, for having me present this and for funding it. And I would also like to thank all the students that helped with this project. This is only some of the names. There are a lot more people that were involved in this. Basically, I had 15 students helping me. The take home from this is when this hydroxyseleniumethionine is administered at the same level, we get the same effect that we get with selenio yeast. So selenium, we all know, is an essential mineral that if deficient in the soil will therefore be deficient in dairy cows. And for the Northeast, this is very true. Supplemental seleniums exist in organic and inorganic forms. The organic are selenio yeast, and then the seleniumethionine or hydroxyseleniumethionine. Those were the two we looked at in this trial. The overall objective was to determine the amount of selenium that was transferred to milk and blood in mid to late lactation cows when we supplemented them with either the hydroxyseleniumethionine or the selenio yeast. We also had a control group that was the control diet. So we had 24 cows, we had 12 multiparous and 12 primiparous. It was a replicated random block for 13 weeks. The first week was covariate, the last 12 weeks were for treatments. The treatments were basal diet or negative control, which will be designated as NC. The basal diet plus 0.3 milligrams of selenium from selenio yeast, which is the positive control, it's SY 0.3. The basal diet plus 0.1 from the seleniumethionine, and that's SEMET 0.1. And then we had the 0.3, which we designated as OHSMET 0.3. The basal diet was formulated to have a background of 0.2 milligrams of selenium per kilogram of feed fed. And this was a diet that we fed. It's a very typical diet for the Northeast here. Unfortunately, we should have had a 0.2 instead of a 0.5. We found out as we were running this that our mineral was contaminated with selenium from natural sources that we had no control over. So milk yield and dry matter intake were determined daily, averaged by week. Milk samples were collected in the last 3 days of the covariate week and week 1, 2, 3, 4, 6, 8, 10, and 12 of the treatment weeks. Also in that time frame of the 3 days of the covariate and then the 3 days of week 1, 2, 3, 4, 6, 8, 10, and 12, we collected blood samples. The data was analyzed using the mixed procedure SAS with repeated measures. The fixed effects were level, week, and block. The random effect was cow within block, and significance was noted at p less than 0.05. So now I'm going to move on to the results. If you look at milk yield, there was no difference among the selenium treatments. They were all significantly higher than the negative control. When you come down to milk protein, we see that for some reason the positive control was significantly lower. We're not 100% sure why there. The interesting part was down here at the linear somatic cell score, the 0.3 selenio yeast, seleniumethionine, we had a 0.1 where everybody else was up closer to 2. And for energy corrected milk, once again, the 3 sources of selenium were significantly higher than the energy corrected milk. I'm going to show you the weekly differences here for the linear somatic cell score. So here's our seleniumethionine, hydroxyseleniumethionine. As you can see, they all started out very similar, a little bit higher here, a little bit lower here, but by week 2, these guys had dropped significantly and stayed down low, whereas everybody else was up high, except for week 10, where everybody took a dip and then went back up. These is the plasma and milk results, the selenium in the plasma and milk. These were a little bit higher than what we thought. Once again, it had to do with our basal diet being higher in selenium than what we thought. So we get the highest amount of selenium with the seleniumethionine. and then we get it with the selenio yeast, and then this is just the seleniomethionine, and then the negative control. Same thing occurred in the milk. So our highest was with the seleniomethionine, then the positive control, then our 0.1 value, and then our negative control. The glutathione peroxidase activity was not different among the groups. So this meant that we weren't really getting any more activity by feeding a better form of selenium. So once again, here's our plasma by the week. And as you can see, the 2.3 seleniums, we stayed high where the other ones start to decrease. This is our milk. This we cannot explain. We've sent the samples back for reanalysis. They come back with the same amount of selenium in them. So this is a mystery to us. But everybody else, if we get rid of this, we've kind of had a nice selenium, high in the beginning when they were earlier in lactation. As milk production dropped off, the selenium in the milk decreased. This is the glutathione peroxidase. It kind of increased over the time period, but it was not different among treatments. So in conclusion, these results confirm that organic selenium forms can increase milk and can increase selenium concentrations in milk and plasma. In the hydroxyseleniomethionine, lowers and maintains a lower somatic cell score, which in virtue means lower somatic cells, but when administered at the same level of supplementation, the seleniomethionine was shown to be more efficient than selenio yeast at improving selenium concentrations. And with that, I'll take any questions.
Thank you, Nancy, for your presentations. I have a couple of questions in regards of the dairy diets. You started your statement that dairy diets are deficient in selenium. Is that correct for everywhere, or my understanding? The reason I'm asking this is because my understanding is that depending on some regions of the country, you may or may not bring more or less selenium to the diet of the dairy cows.
That's true. I mean, the Northeast is very selenium deficient, and I think parts of the Midwest are, but then other parts are not, so you wouldn't really be feeding extra selenium.
Okay. Another question I have, Nancy, is my understanding is that selenium is the only mineral that is regulated by the FDA. And it's being regulated to these 0.3 parts per million per kilogram of dry matter. Now, is that? I mean, that doesn't seem really reasonable based on this information that you just show us in here. That the depending on the source of selenium you're adding to as a supplement to these dairy diets, you may or may have more selenium delivered to the dairy cow.
Right. You also have to remember, even though selenium is an essential mineral, it's also a toxic mineral. So when you get too high, you can cause toxicities. And the biggest concern is that we have too much selenium in if we're feeding selenium to the dairy cows, we get too much selenium in the milk, and then we're passing it on to consumers. So that's one of the reasons the FDA has put in that 0.3. They know when you're feeding this stuff, it's going to go a little bit higher, but if they put it at 0.5, then we could be getting into some toxic effects.
My understanding was, and maybe we can leave this for at the end of the presentations, but since we're in this topic of toxicity, my understanding again was that the sources of the toxicity of selenium, one of the issues when this 0.3 parts per million was set was because of the potential carcinogenic effect of selenium. But the sources that are being fed to dairy diets are not the ones that are cancer. So I mean, I know that some people have been questioning and some people are pushing for maybe raising that number up, considering the potential benefits of feeding selenium to cows. Any comments on that?
That's all up to the FDA, Daniel.
Yeah.
I have no control over that. It'll be interesting. I mean, this was an FDA trial for the seleniomethionine hydroxy product. It'll be interesting to see what the FDA says. I don't know if they've gotten back to people at Adisseo yet or not. We submitted that back in, I think it was February or March, because we knew that the levels were high. So it'll be interesting to see what they say, because we had you guys aren't seeing all the data, but we had no adverse effects on these cows. So like we measured all the blood metabolites, so like neutrophils and basophils and platelet counts and the liver enzymes and all that, and nothing was elevated to the point where we were causing problems with these cows. And you gotta remember, these cows were on it for 12 weeks and they were late lactation cows. The only thing we did see was that benefit with somatic cells.
Yeah, and this is another topic, and maybe we can leave this for Michele, our next presentations. To some of those questions have come to him, but he's been involved with this research for much longer time. We will bring him to the next speaker. So maybe he could address some of these questions, Nancy, as well. Thank you very much.
Okay. You're welcome.
Yeah. So our next speaker is Michele De Marco. Michele is an Adisseo employee, and he's been involved in these projects since the very early stages. He's based in France. Michele, you are on, and I can see your presentation. Thank you.
So thank you, Daniel, for the nice introduction. Hello, everyone. Thank you for joining this Adisseo virtual roundtable. As Daniel said, my name is Michele De Marco. I'm Italian, and I'm working here in France, in Paris, as a global technical manager, mainly focused on selenium and on hydroxyseleniumethionine, better known as Adisseo. So today I will present you some preliminary data coming from a trial that we carry out with with my colleagues in France, where we aimed actually to provide some new knowledge around selenium additive metabolism in ruminants and in dairy cows. So to start, I would like you to consider the following question. Is dietary sodium selenide transformed into elemental selenium by rumen microorganism? So now we will see what we discovered. So just to introduce the topic, as Nancy said just before, selenium is an important trace element for endocrine reproduction and antioxidant systems in animals. Today, there are three main families of selenium additives. There are the historical and mineral form, mainly sodium selenide, that have been authorized in 1979 in US, but are still widely used as a selenium supplement for livestock. Since the year 2000, arrived in the market the so-called organic form of selenium, and this organic form are mainly selenium yeast, so yeast that are enriched in selenium. And when they have been launched in the market, it was a big revolution in the selenium nutrition, because they were the first form of selenium able to provide selenium in the form, part of the selenium in the form of seleniumethionine. And then since 2014 in Europe, and since last year in US, arrived in the market the so-called pure form of organic selenium, that are actually form of selenium that are produced by a pure chemical synthesis and are able to provide 100% of the selenium in the form of seleniumethionine, or in the case of Adisseo, in the form of hydroxyseleniumethionine. When we talk about selenium additives, we know that the mineral form of selenium are well known to have a lower bioefficacy as compared to organic form of selenium. And this pure bioefficacy, it has been already largely reported, but is still poorly understood, particularly in ruminants. And limited results present in literature showed that this lower bioefficacy can be related to the formation of some elemental selenium in the rumen. So to answer these questions, we carry out trials in our experimental facility in France with the aim to evaluate if feeding dairy cows with sodium selenite or organic form of selenium leads to the synthesis or the creation of some elemental selenium in the rumen juice. So basically, we used 11 rumen cannulated Holstein cows that have been divided in 4 groups. A group was fed with a negative control diet based on hay and protein and energy concentrate, but without any supplemental selenium. And then the other groups were fed the same negative control diet, supplemented with 10 milligram of selenium per cow per day, either in the form of sodium selenite or in the form of zinc selenium-methionine or in the form of hydroxy selenium-methionine Adisseo. The cows followed an adaptation period of 7 days, where they were fed the negative control diet, and then they were split in the 4 feeding groups for 22 days. And then after 22 days of a feeding period, some sample of blood were collected at 22 days, and sample of rumen fluids were collected at 22 and 23 days to evaluate the level of selenium and the recovery of elemental selenium. So now let's move to the results. So as you can see, in these 2 graphs are reported the level of selenium recovered both in the plasma samples and in the rumen fluid samples. In the upper graph, you can see that the 2 organic form of selenium, so zinc selenium-methionine and Adisseo, led to have the highest amount of selenium transfer into the plasma as compared both to the sodium selenite fed groups and the negative control group. And the same was detected in the rumen fluid, where also in this case, the 2 organic form of selenium led to the highest level of selenium transfer in the rumen fluid. And by comparing the 2 organic form, Adisseo was the form leading to the highest transfer. Interesting to see is that when we correlate the data that the selenium recovery in the plasma and the selenium recovery in the rumen fluid, there was a very high positive correlation, meaning that the recovery and the analysis of selenium into the plasma is well correlated and is completely explaining what is also happening in at the rumen level. And we can see here the square R was 0.96, so very high positive correlation. And when we did the selenium speciation in the rumen fluid sample, where actually we analyzed all the 4 samples for the recovery of elemental selenium, we saw that only in the group of cow that were fed sodium selenite, we were able to recover, there was only in this group the formation of elemental selenium, something that we were not able to detect in the cows fed the negative control diet or the diet supplemented with zinc, selenium, methionine, or with Adisseo. And then we saw that the elemental selenium in the sodium selenite fat group represented about the 42% of the total selenium analyzed. And then when we evaluate in which fraction of the rumen fluid this elemental selenium was more present, we saw that the highest amount of elemental selenium was detected in the fiber fraction of the rumen fluids. So, to conclude, we were able first to see that organic selenium forms lead to the higher transfer of selenium in the rumen fluids and consequently into the plasma, and in particular, hydroxyselenium methionine was the form leading to the highest transfer of selenium both in the rumen fluid and in the plasma. The selenium level in the plasma, we saw that it was proportional to the selenium level measured in the rumen fluids. This means that the total selenium in plasma tell the truth, and it is a very good biomarker to evaluate the selenium status of our herds, but at the same time also to evaluate what is actually happening at the rumen level when we fed different types of selenium additives. And last but not the least, we demonstrate and we confirm some old data about the fact that sodium selenite is partially reduced into elemental selenium in the rumen, which partly explain the lower bioavailability of this mineral form of selenium in ruminants. And with this slide, I will end my presentation. I will be glad to take your questions. Thank you.
Thank you, Michele. Is this the view from your house?
Sorry?
Is this the view that you have from your house?
Unfortunately not, but it's not far from my house, to be honest.
No, thank you for your presentation, Michele. It was great. I do have a couple of questions.
All right.
Is this maximum level, the 300 milligrams per kilogram of dry matter, is this the same for all species, or is just for dairy?
No, it's for all species. Actually, worldwide, we are limited in the selenium supplementation at 0.3 ppm per kilogram of feed or per kilogram of dry matter intake. And we cannot go above the 0.5 ppm of the complete feed or the complete ratio. And this is something that is common for all the species, so monogastric or ruminants. And we have a main difference between Europe and all the other countries all around the world, because in Europe, actually, the limitation is more strict, because in Europe, we can just provide 0.2 ppm as organic selenium.
Because they are essentially taking into account the higher bioavailability. That's the reason why?
Yeah, in Europe, this is the reason why. Yeah, but okay. In US, the limitation is the same if you supplement selenium in organic form or in inorganic form, because normally the authorities, so FDA, takes into account that on average the raw materials can provide between 0.05 up to 0.2 ppm of selenium from the raw materials. So you can normally then add the 0.3 ppm to get the maximum level of 0.5 ppm.
Have you? I mean, for what I know, I mean, the maximum beneficial impact would be for this, or one of the impacts of feeding selenium are two stages in the lactation in the cycle of the cow. One is a transition because of the antioxidant impact, and the other one is on reproduction. Have you run any trials testing this product in transition or to look into the impact in reproduction of the cows?
I mean, so far we did some trials. We also published a paper last year. we were mainly focused actually on the transfer of selenium from the dams to the newborn calves, and we saw that there was a stronger, a significant, highly transfer using Adisseo compared to sodium selenite from the mother to the newborn calves. So actually, through the colostrum, the mother was able to transfer more selenium to the newborn cows, helping them actually to better start compared to the group that was just fed with sodium selenite. And then we have a very positive feedbacks, in particular from countries that are highly deficient in selenium, such as New Zealand. In that case, in that country, the use of Adisseo is quite is now very, very large, because actually there are, dairy cows are mainly on pasture, so, and the soil is very deficient in selenium. So as soon as the farmer they start to use hydroxyselenomethyne, they really saw a strong positive impact on fertility, on conception rate, and also on the quality of the newborn cows.
Perfect. Thank you, Michele. I mean, this is great information, and is obviously an area of research that we should focus and do more work, because of the results and the potential benefits for the dairy producer and the cow are really huge. Yeah. So
just another small comment about what you say before about toxicity. Actually, it's also very important to highlight that the organic form of selenium, so mainly selenium-methionine, has a much lower toxicity as compared to sodium selenite, and this is already very well demonstrated. So also in case of mistakes in the selenium supplementation, selenium-methionine is a form that can that is much more safe as compared to mineral form, because it is proven in different in vitro but also in vivo models that the toxicity of this organic form of selenium is much lower compared to sodium selenite. So it's also safer compared to the mineral form that are still widely used in the market.
Great, thank you for your presentations, both Nancy and Michele. And please hang out until we hang on until we are at the end of all the presenters. So we might, some other questions may come up after we're done with all the presenters. So thank you again for your presentations.
Thank you.
Yeah. Our next presenter is going to be Mateus Toledo. Mateus is from Brazil, and we are lucky that he's alive. He just finished and went over his prelim exam last Friday. I am surprised that he showed up today. But Mateus is working under the supervision of Dr. Milo Wilbank and Dr. Randy Shaver, student PhD candidate at the University of Wisconsin. So with that, Mateus, go ahead, please. Thanks.
Thank you, Daniel. Just to confirm, you're seeing my presentation on the screen, right?
Yes, sorry. Yes, you are.
Okay, good. All right. Good morning, everyone. Thanks for joining this Adisseo virtual roundtable. So for this presentation, we're going to talk about the effects of feeding room protect methionine, pre and postpartum on health disorders and herd exit dynamics in multiparous hosting cows. So there was a large trial we conducted in collaboration with Cornell University. So a lot of people were involved with. I just want to thank all my colleagues in here, especially Matias Estangaferro, which was the leader of the trial in Cornell. All right, so to get us started, just as a brief introduction, so we all know that methionine is a very important nutrient, is a required nutrient, and one of the most important limiting amino acid depending on the type of the diet, and also a functional amino acid. You are looking at the molecule of methionine here on your left, and then on your right, you're looking at a diagram by Dr. Wu showing many functions that amino acid can have. And that's described what a functional amino acid is. On the top, you're seeing a function of protein synthesis. And then besides protein synthesis, amino acids can have other functions. And that's how we say it's a functional amino acid. And methionine is involved with some of them. Just a second. You're seeing a couple here, for example, DNA methylation, and then some of these we're going to talk about today. Methionine can be involved with health as well. All right. More recent studies show some work indicating that methionine may be involved with some health indicators, and those are related with immune function, inflammation, liver metabolism, and oxidative stress. However, those studies do not have a large number of cows to adequately evaluate the prevalence of health disorders. With that, our objectives they were to determine the effect of feeding room protect methionine in pre and postpartum GMR, on prevalence of health disorders, and then also we're looking at if methionine, feeding room protect methionine alleviates the negative impact of health disorders on productive and reproductive performance. This is how we conduct the experiment. We enrolled 470 multi-parous hosting cows, half in University of Wisconsin and then half at Cornell University. Cows were randomly assigned to close-up dry cow and replicated lactation pens, 18 pens. And then pens were randomly assigned to a control or a room protect methionine treatment, whereby the only difference was the inclusion rate of room protect methionine. This table is just showing you the estimated CNCPS amino acid supply. We have the two locations and then pre and postpartum. I just want to show you the difference between treatments. Prepartum, we have a difference about 6 to 8 grams of metabolizable methionine. And then postpartum, we have about 14, 15 to 18, 19 grams. This is a postpartum diet chemical composition. Some minor difference between the two locations, but overall, very typical Midwest and Northeast diet, crude protein about 16.8%. This is our experimental design. You're looking at our timeline. Before calving, we enroll cows and then fed treatments until 147. Cows were enrolled in a double off-sync protocol. And then the two pregnancy diagnoses at day 32 and 67. And then you follow those cows until 350 days in milk. This is where we recorded all the health disorders, ketosis, retained placenta, mastitis, respiratory problems, and lameness. That was until 147 days milk. Uterine cytology was performed at day 35 after calving. Milk yield daily and milk composition was biweekly. And then time to pregnancy and cows that die and were sold, that was recorded up to 350 days in milk. In addition to this, we classify cows based on health disorders number, cows with no health disorders, cows with a single health disorders, and cows with multiple health disorders. For all those analyses, PEN was the experimental unit, and then we previously report productive and reproductive performance in previous ADSA meetings. Just want to show you how feeding room protect methionine increase plasma methionine. To do this in this study, we collected blood samples from a subset of cows, 72 cows, and that was within 3 hours after feeding. Cows were at mid lactation, not early lactation, 80 days in milk, and then we individually analyzed for free amino acids. This is the average, so there was a treatment effect. For cows fed room protect methionine, 35.7 micromolar, and then for cows under control, 21.6. That's the average, but I just want to show you what's interesting is the variation that we see individually here. We see a lot of more variation for cows fed room protect methionine. You're looking at coefficient of variation for the control, 22.2%, and then for the cows fed room protect methionine, 29.5%. Moving on to the proportion of health disorders, we're looking at first all the categories, cows with none, single, and multiple, and then the control and the room protect methionine. You look at the number of cows there, 237 for the control and 233 for the room protect methionine treatment, and then p-values for treatment and farm. And then below here, we have each type of health disorder. Okay, and then on the bottom, we have uterine health. We did not observe any effect of treatment in any of these category, type of health disorder, and uterine health. There was a cytological endometritis at day 35 after calving. This is the productive performance by health status category. You're looking at the 3 categories, and then within each category, we have control and room protect methionine, and then the p-values for each category. We did not observe any effect for milk yield, energy correct milk, and energy content in milk. However, when you look at milk components, we see some increase in cows with no health disorders, about 30 grams, but that's not significant. For cows with a single health disorders, there was an increase about 50 grams. There was a tendency, but we saw a greater effect when cows had multiple health disorders, and there was about 80 grams of milk protein. In addition, for milk composition, we saw an effect, an increase in milk protein percentage for all those 3 categories. In addition, the time to pregnancy after calving, this is a survival curve analysis. You're looking at the proportion of cows pregnant, and then on the x-axis, the time after calving. Comparing cows with no health disorders and cows with multiple health disorders, you look at a hazard ratio. So cows healthy, they had a little bit more than 2 times more chance to get pregnant earlier, right? And then when you look at the median days to pregnancy, for cows with multiple health disorders, 151, and cows with no health disorders, 83 days. So it's a huge difference in time to pregnancy. When we compare treatments within cows with no health disorders, we saw the same hazard ratio, so they were getting pregnant at the same time. However, for cows with at least 1 health disorder, we saw a hazard ratio of 1.38, and then cows fed room protect methionine, they were getting pregnant earlier, and that was about 23 days. Moving on to herd exit dynamics, you're looking at the cows that were sold, died, and left the herd. That's just a sum of sold and died. We observe a tendency for a decrease in the proportion of cows that were sold when we feed room protect methionine, and that was up to 350 days in milk. Below here, we're just looking again at a survival curve, just showing that the cows in the control group, they were sold earlier compared with the cows fed room protect methionine, and then the hazard ratio that was 1.5. Just summary and conclusions. So treatments had no effect on any type of health disorder recorded. We observed improved overall milk protein production, and that was particularly in cows with health disorders. In addition, it appears to reduce time to pregnancy in cows with at least 1 health disorder and may decrease the likelihood of cows being sold. But of course, you need future studies to confirm these results and determine the mechanisms whereby room protect methionine may alter pregnancy viability and likelihood of cows leaving the herd. That's all I had. Thank you, and I'm open for questions, Daniel.
Thank you, Mateus. Really nice presentation. I know that it's hard to assess the impact of health disorders and the number of cows that you need for treatment and so on and so forth.
Right.
I just have a couple of questions. Why is the coefficient of variation of the plasma methionine larger for the cows that have been fed rumen protected methionine compared to the control cows? It looks like there was much more spread on those cows.
Yeah, that's a very interesting question. So we're not sure why we see that variation, but it can be many things, right? It can be a dry matter intake only, which is one thing that we did not record. We just had pen dry matter intake. It could be also metabolism, right? So cows are using methionine different. So there's a couple possibilities, and we need more intensive studies to try to study the metabolism of methionine and their variation, why that happened.
Okay. As you mentioned, it seems to be that the cows with higher incidence of diseases, it's not that the cows fed rumen protected methionine had higher milk protein, is that the cows with higher incidence of diseases lower their milk protein content. Can you speculate why is that?
They lower their milk protein content. It looks like because numerically you see a higher milk yield, but milk production is higher for cows with multiple health disorders. Is that what you're asking?
Well, I mean, you had a difference, a significant difference in terms of grams of milk protein in the cows that were fed, but
yeah.
Those were the same. I mean, what about if I recall, you can go back to your slide number 9. I think that's the slide that you showed in that table. Yeah, that slide there. So essentially, you had 80 grams more protein per those cows, but it's not that those cows produce more protein. It's that the control cows had less milk protein,
right.
total grams of milk protein. So I mean, is that because methionine was? Can you speculate? And I don't want to put words in your mouth, but is that because methionine was used for some other purposes in those cows?
I mean, this is just to say this is just a correlation, right? It's not a randomized trial where we are testing this. It's a correlation. It looks like for those cows with multiple health disorders, I don't have the p-value here, but you see a difference. If you look at the control, there's 100 grams of difference.
Okay.
So for cows that are sick, it has a huge impact on production, right? Okay. And then when you feed a couple of grams of more methionine, it seems that those cows, it could be they were more deficient in methionine, and then methionine can help with health somehow, and then that results in improving in protein production. Okay,
great, thank you. I mean, obviously, there are many things that we are still learning about the mode of action on methionine and how the cows use this and how they divert all these amino acids to help them out. But this is great information, Mateus. Also, I mean, the cows' time to pregnancy. I know that there was not significant value there, significant difference there, but it is a good number of days difference in there. So it looks like I mean that's it's a really nice important value to take a look at it in terms of the economic importance of this. So.
Yeah, exactly.
So anyways, this is a great presentations and great information, Mateus. We're going to move on because we are about a few minutes late now. And I'm going to move on into the next presentation, which is about mycotoxin by Dr. Nancy Whitehouse. So Nancy, if you can share your presentation, and we will go with your presentation.
Once again, thank you for having me come this morning. And this was also sponsored by Adisseo. It was a mycotoxin deactivator that we looked at. I'd like to thank Ben Kearns and Hannah Robertson. They both did this as part of their senior thesis because there was a lot of work involved in this study, and they chose to do it as their senior thesis. Overall, we found out that mycotoxin, when we fed the mycotoxin deactivator, it improved dry matter intake and energy-corrected milk yield, increased monocytes, but had no other effect on the other immune cells when we fed a natural mycotoxin. And you'll see what that is in a second. So mycotoxins are secondary metabolites produced by molds. Mycotoxin contamination of feeds pose a serious health effect to dairy cows. We normally will see decreased intake, decreased production. You have an impact on the immune system, and you also see decreased fertility. We did not look at the decreased fertility in this study. So the objectives of the trial was to determine the effects of a mycotoxin deactivator on lactation performance and plasma leukocytes in dairy cows fed a mixed mycotoxin contaminated feed. So we had 24 cows. They were mid-lactation. It was a replicated randomized block. We had 7 weeks, 1 week for covariate and 6 weeks for treatment. Our treatments were negative control, which we'll designate as NC, positive control with a mycotoxin exposure from contaminated distillers grains, which we call PC, and then the PC diet plus 60 grams of a mycotoxin deactivator is UNEC plus from Adisseo, and we're going to designate that as UP. And the mycotoxin was composed of clays, yeast, antioxidants, and herbs. This was the diet that we fed. Once again, it's a typical Northeast diet for us. We did add smartamine M and Agipro-L to make sure that the cows were lysine and methionine adequate, so that was not going to be a consideration in this trial when it came to the health indicators. So milk yield and dry matter intake were determined daily, averaged by week. Milk samples were collected on the last 3 days of each week and sent off for analysis. Blood samples were collected from the coxial vein for 3 consecutive days on the end of the covariate, week 3 and 6. And it was run on a veterinary hemological platform to look at the immune responses. Data was analyzed using the mixed procedure SAS with repeated measures. Fixed effects were treatment week and treatment by week. Random effect was cow within block, and significance was noted at p less than 0.05. So we're going to move on to the results. This was what we looked at for mycotoxins. So this was our control diet. This was our distillers grains, which was what we were feeding as the natural mycotoxin. And then this is the TMR. And then this is the contaminated. These are also distillers grains. These had very low mycotoxins. They came from the same part of the country, but a different facility. These were the high distillers grains, and this is TMR. And as you can see, with the fumicin, we did have a lot in the distillers grains. When it came to the TMR, it was lower because it's being diluted out. The zealanine and the vomitoxin, this was the one we were really looking at. So as you can see in the distillers grains, we had a lot of it. But it was diluted out a little bit in the TMR just because of the other things we're feeding, but it was still fairly high. So for dry matter intake, you can see when we fed the positive control, which is those distillers grains, we did get a trend toward a decrease, and we had a treatment by week interaction. When it came to milk yield, we didn't really have anything. We had a treatment by week again, which I'm going to show you in graphs in a minute. Energy corrected milk, same thing. And then when it came to somatic cells, the negative control was the lowest, with our 2 mycotoxins being the highest. So dry matter intake, this is the graph. So you're going to see what I'm looking at. On the y-axis, week is going to be on the x-axis. The negative control is blue. The positive control is this brownish orange, and the mycotoxin deactivator is a gray. So there was a difference right off the bat at week 1, with the negative controls being a little bit higher than the 2. Then they all kind of came together. But down here, you can see our positive control really starts to drop off on us, with these two staying similar, and then it starts to come back up at week 6. When we look at milk yield, once again, we see, the negative control is a little bit higher than the other two, with the positive control being in the middle. And things are pretty much similar until we get out here at week 6, where we see this positive control just drop off on us. And then when it comes to energy corrected milk, it's even more exaggerated. We actually start to see that drop off for that positive control, which has nothing in it, starting at, I really think it starts at week 4, but it doesn't turn significant until week 5. And it really goes down week 6. And we're actually getting, when we feed the mycotoxin binder, we're getting a little bit more energy corrected milk versus the negative control here. And then somatic cells, here's our negative control. It's always down low. And then something's going on between week 5 and 6. We see that positive control really start to go up, with the mycotoxin binders being in the middle. And then when it came to the leukocytes, we looked at neutrophils, lymphocytes, monocytes, and then overall leukocytes. And as you can see, there's a trend for a decrease in neutrophils with the positive control. Nothing with the lymphocytes, but with the monocytes, we definitely see those are decreased. And a decrease in monocytes usually indicates that there's some kind of infection going on, because these guys are going in and, like this shows, it's killing off whatever it is. And this could all be something to do with that somatic cell stuff going on, because that was, or some other health issue that we could not pick, we did not see. So adding a mycotoxin deactivator did improve dry matter intake, energy corrected milk yield. It increased monocytes, or you could say when we didn't feed it, there was a decrease in monocytes, but it had no effect on the other immune cells. We did take rumen samples in this trial, and that is currently being processed. Due to COVID, our lab that processes stuff for us is now doing COVID related work instead, so things are kind of on hold there. And we do need to do further research, because this was a very short time. It was 6 weeks, and we were starting to see stuff occurring at week 5 and 6. We really think this should go out to like 12 or longer, to see, does the microbes, they say that microbes can kind of take care of some of the toxins. Do they? Or is this, if you keep feeding this, is this going to have a long-term impact on your cows? So with that, I will take any questions.
Thank you, Nancy, for your presentation. This is very timely as well in terms of the impact of mycotoxins. I just have one question regarding, do you have any explanations why the impact on dry matter intake of the cows?
I don't really, unless it's something to do with the, we really don't know what's going on with the microbiota. So that will be interesting to see if there's something going on there that's decreasing the intake of these cows, or is it a palatability thing? I mean, I don't really know what it is.
Okay. Is there, when would you, obviously there is an impact on mycotoxins on the overall production of the cows. When would you recommend dairy farmers to include these products into their TMRs? Or what parameter would you use?
I would actually, just because we don't know what effect it really has on those microbes and the overall health, I'd be feeding it up in when you're feeding your dry cows, because sometimes, dry cows don't get the best part of the diets. Definitely through transition, definitely in early lactation. Personally, here at UNH, we feed a mycotoxin binder year-round to everything, except for our baby calves because they're on milk. But once our animals go onto a TMR, they are getting a mycotoxin binder. We do see a lot of mold in our corn silage and some of our haylage just because of the weather we have and we're trying to put it in. So it was just cheaper for us to add the mycotoxin binders versus, dealing with the health effects. Because there is some research that shows, and I haven't seen it, but some of these, especially the aflatoxins, which luckily we don't have here in the Northeast, can cause animals to die, can cause abortions and things like that. So out in California, where aflatoxins are a big problem, definitely be feeding binders.
Do you test routinely test for the presence of mycotoxins in your silages or your feeds that are purchased out?
We don't test our feeds because that's done by the company that supplies our feeds. So they routinely test their feeds. We never used to test our hay crop and corn silage, but now if we notice that we're having some animals going off feed or so forth, we will send it out. Or if we notice we are seeing, funky things in the feeds, we'll send it out and see what happens.
Okay. Okay. Well, great. Thank you. We are a little bit over of the time that we have allotted for the four presenters. So what we're going to do now is we're going to essentially see if there are any general questions for all the presenters in terms of the four presentations given today. Obviously, more focus on health, the impact of nutrition on health of the cows. So any questions that might be coming out from the audience? And again, you can type your questions, otherwise you are all on mute. I do have one question, and this is more related to Mateus, and it's essentially, does the cow has a requirement for methionine to make sure that all her needs are met to maintain her bioavailability in the herds? So I mean that's a question for you, Mateus.
Yeah, interesting. Yeah, we don't feed methionine with a requirement for health and reproduction, right? I mean, that's based on milk protein production, right? So I think we need a lot of studies still to understand what's the dose and what's the amount of methionine needed for the cows to optimize all the three: health, production, and reproduction. So yeah, we don't. It's a required nutrient, but we still don't know what's the requirement for health and reproduction optimization.
Great, thank you. And now I'm going to go back to the selenium questions. Right now, I mean, there is a lot of there are not a lot, but there are some information that the cows in transition can benefit for using selenium, a little higher doses of selenium in transition. And also, there is a lot of interaction of the availability of selenium in the basal diet, particularly when depending on the amount of sulfates and so on and so forth. Is anybody working on that, or is that being seen by any of the nutritionists?
Yeah, thanks for the question. So basically, to answer to your first question, the fact that we are limited in the selenium supplementation, this means that we cannot go above the threshold set by FDA or the European community. However, there is more and more result coming from the literature showing that sometimes going ahead of this value, you can get some extra benefit in terms of fertility or production, for example, during stress situation. And the fact that with organic selenium, we are able to provide selenium methionine that can be stored, so can create a kind of a selenium pool. This is a key point, because creating this selenium pool in the body of the animals, then the animals, when they require more selenium to cope with different oxidative stress or with higher requirements in terms of selenium protein due to high production or due to specific physiological situation, they can start to utilize this selenium that is stored in different tissues to fulfill the higher selenium protein and selenium requirement that they have in a specific moment.
So is that it would be advisable then for people to, and I'm pretty sure that people are doing already, but considering really feeding the importance of feeding selenium then in the transition cows, in the pre-fresh cows, to kind of, as you were suggesting, build up that amount of selenium. Okay.
Yeah, actually, is really the reasoning behind the organic selenium concept is to feed in the animal, creating this kind of a selenium insurance policy in the tissue, because it's selenium methionine, the part that is not immediately used to fulfill the immediate selenium requirements, is not excreted as a mineral form, but is stored mainly in skeletal muscle. And then when animals are facing a specific stress condition, as I say, related to physiological conditions such as the transition period, the transition period, or due to specific environmental challenges such as stress. During this stressful moment, there is also higher protein catabolism. So there is some selenium methionine that is released from this muscle and can enter again in the transsalination pathways, helping the animal to maintain the synthesis of those selenium proteins, or to increase the synthesis of those selenium proteins to fulfill the animal requirements.
Another question is if the needs for selenium increase, is there a direct correlation with the needs for increased vitamin E?
Not really. I mean, of course, vitamin E and selenium are both very important antioxidant. They are both working, I would say, in complementarity in the organism, because are both involved in the antioxidant system. However, I would not say that we need to increase both. Normally, is something that we are seeing some other species, is that sometimes we can, using the right form of selenium, so maximizing the selenium pool in the animal, sometimes we can also slightly decrease the amount of vitamin E, because we can, with selenium, some selenium protein are also involved in the recycling system of the vitamin E, so you can actually maintain maintain the efficacy also of the vitamin E that is reduced due to the all the redox reactions that are happening in the body.
Great. Yeah, we can learn. I know that you have extensive experience with the other side of the equation here, not dairy cows, but monogastric. So yeah. I guess that I was kind of trying to pick your brain in terms of what our poultry or swine colleagues are doing. Are they seeing these effects in health and reproduction when they feed more selenium or resistant to heat stress?
Yeah. I mean, there is, the organic selenium concept is now very well established, particularly in breeders. So in breeding animals such as poultry breeders or in swine in sows, and the main benefit of organic selenium are mainly on fertility and on reproduction. And now there is more and more proof of the fact that using the right form of selenium, so maximizing this pool of selenium, this selenium reservoir in the body, helps also animals, no matter the species of ruminants and monogastric, to cope with external challenges, such as one of the main environmental challenges that animals are facing year by year is stress. And on that, there is already a good body of evidence that using organic selenium, you can really help animals to maintain a better performance. I mean, it's not something that is improving the performance of the animal, but using organic selenium helps the animal to maintain a better performance during stress, for example. We have an example. There was a paper that was published in 2018. And in that case, it was an external research made by some researchers that were not connected with Adisseo. In that trial, they tested they compared sodium cyanide with Adisseo in a stress model, and they saw that for the same drop of dry matter intake, the cows that were fed with Adisseo, they were able to significantly maintain higher milk yield during the stress period.
Perfect, thank you. Well, I'm glad that you brought back to the dairy cows, and I thank you so for your answer. I mean, we need to pick your brain more in terms of reaching to your experience. I'm going to go. Yeah, go ahead. Sorry.
No, and then it's also something that on the effects on health of the animals. We also see the study that Nancy just presented in the first presentation, where we saw that actually using Adisseo at 0.3 ppm, we were able to maintain the lowest level of linear somatic cell count in the milk. So it's also something that we also see in the field. Actually, when customers are using Adisseo, they are able to maintain a lower and long-term level of somatic cell count in the milk.
Great, thank you. Well, I'm going back to the health issue overall and the impact of these different required nutrients. One more question for Mateus. Essentially, is there? Do you think that the needs for methionine can increase to cover all these extra functional needs of methionine for dairy cows? To cover for to make up for these needs for as you indicated earlier today, we're looking into feeding methionine to make up for the milk protein content or milk fat content, perhaps, but we are never have seen methionine as a nutrient that would help the cows to stay in the herd. But if you can prevent having all these health and reproductive issues, shall we feed more methionine to cover for those?
Yeah, interesting question. Thanks for the question. Yeah, we are not sure what's the perfect dose of methionine for optimized health and reproduction. We know that if you're balanced diet to optimize protein production, and then cows are in a situation of stress, you may get some improvements in the time that the cows stay in the herd and reproduction time to pregnancy. So this is I think the first study. We need more studies to confirm that response. And also, if you feed a few grams more methionine, if that's gonna optimize health and reproduction.
Okay, great, Mateus. Yeah, I mean, there is more that we need to learn, and for the impact of overall impact of nutrients on health and reproduction of the cows. That we still a lot of work to do. But I think we are much past the time that we are allowed to the audience to stay with us. I really appreciate everybody. Just again, we are going to have these sessions are recorded. So if you want to take a look back and take a look at them, they are in feedchannel.online, and we see you. We have 2 more sessions to go, one on Thursday and one on Friday. Thank you, everybody, for sticking around.